Welcome back. Today we will continue discussion on some related topics of 1D wave equation. So, I briefly discuss first order systems. So, now we consider such a system. Let me write equal to. So, again t is a positive real number and x varies over the real line. So, it is a first order system in one space variable. So, here u is a column vector un and A is an n by n real matrix. So, if you expand this, so this we have written in matrix notation. If you write component wise, then it is d by dt of ui is equal to summation j equal to 1 to n aij d by dx of uj. So, there are n first order equations. So, that is why it is first order system. So, aij are the components of the matrix. We assume that, so this is basic assumption, assume that A has the matrix A has only real eigenvalues. As you all know, even a real matrix can have complex eigenvalues. So, this is an assumption we are doing on the matrix given matrix A. With these assumptions, so let me call this system as 1. So, system 1 is called hyperbolic. With these assumptions, so that is important, with the above assumption. Further classification of system 1 is possible depending on the nature of eigenvalues and the corresponding eigenvectors. That really takes us into some deeper aspects of the theory which I am not going to do. For the purpose of just illustrating the applicability of several methods we did in this chapter, I just restrict myself to the case when A has just eigenvalues. I will not even assume that they are distinct or whatever, they are just real eigenvalues. In that case, again from linear algebra we learn that, so if a real matrix has, so this is from linear algebra I am recalling, has only real eigenvalues, then it also has real eigenvectors and generalized eigenvectors. So, it is good time to recall all these notions from linear algebra. Generalized eigenvectors. Okay, so that is from linear algebra. So, therefore, there exists a real non-singular matrix C such that C inverse A C is a Jordan matrix, call it lambda, where lambda we usually write it as J1 Jk is a Jordan matrix. So, this is called this is the Jordan decomposition theorem. Okay, so, this is one of the important and very deep theorem of linear algebra. So, it is important that with the assumption that A has only real eigenvalues, we are going to get a real non-singular matrix. That is important for us, because we are looking only for the real solutions. Okay. So, this J1, J2, Jk, so are Jordan blocks, a typical Jordan block. Let me write typical Jordan block is a square matrix. So, I am using both. So, this is also a matrix notation. So, let me just write square brackets. So, on the diagonal you have same lambda and all the elements in the below the diagonal are 0 and just 1 on the diagonal just above the diagonal subdiagonal, so, and then again 0. Okay. Very simple form. It could be 1 by 1. So, in that case we have just just lambda. Okay. So, for 2 by 2, so we get lambda 1 0 lambda. So, these are typical examples. So, this is 1 by 1 Jordan block, which is just one element, and this is 2 by 2. Okay. So, what is the advantage of this? The advantage of this is the system 1 reduces to a simpler form, which can be easily analyzed. So, put V is equal to C inverse U. Then let us compute d by dt of V. So, since C is constant matrix, so we can just bring it out and use system 1. So, this is C inverse A du by dx, and again you write in terms of V. So, C inverse A C. So, U is C V. Okay. So, I write it here dV by dx, and this by Jordan decomposition theorem, that is expressed as a Jordan matrix. So, del V by del x. So, this this change of variable reduces the system 1 to a simpler form. So, namely, so let me again write it. So, V t is V x. So, now if you look at the structure of lambda, so they are all Jordan blocks. So, we decompose V as V 1 etcetera V k, okay, according to the orders of the matrices J I equal to 1. So, for example, if J 1 is 2 by 2, then this V 1 will have 2 components. Okay. So, since this is a this implies we can write down a system for each of these components. So, del V I by del t is J I del V I by del x. So, I is equal to 1 to k. 1 to k. So, in this way we have partially decoupled the system 1 into more or less diagonal. So, if for example, A is diagonalizable, then this lambda would be a diagonal matrix, and then this will be a completely decoupled system. Okay. So, if you again write, again look at the typical Jordan block, it is of this form. So, each component therefore, each component of V satisfies a first order homogeneous or inhomogeneous equation. So, let me just write one component V I. So, this del V I by del T equal to lambda I del V I by del x or del V I by del T equal to lambda I plus something inhomogeneous. Okay, this is a function of x t no. So, in either case we can just use the method of characteristics and write down the solutions. So, again remember, so I did not stress that. So, this lambdas, this the lambda. So, this J1, J2, Jk. So, each one will look like this, there is a lambda there. So, they involve different eigenvalues of lambda. So, lambda is a typical eigenvalues of A. So, they all come there, they all come in the diagonal of this matrix lambda. So, they are all eigenvalues of A. So, in this context the eigenvalues in this context the eigenvalues of A play the role of speeds of propagation. Okay, let me now present some examples of various things we did in this 1D wave equation. So, in general the computation of the matrix C and obtaining this Jordan form is a very difficult task. So, more or less easily done for 2 by 2 systems, even 3 by 3 systems, okay. But once you go beyond third order, then computations become very heavy, but in principle, as far as theory is concerned, it is very nicely fits here, and we can decompose the given first order system into more or less a diagonal form. Okay. So, let me show you some examples. Okay. So, various examples I have. So, let me start with D'Alembert's formula. So, this is the wave equation we studied this far with the given initial data. So, here I have taken some very simple initial values. For example, if you take u 0 equal to x and u 1 identically 0, and then the D'Alembert's formula give the solution u x t equal to x for all t positive. So, we may call this standing wave as it does not change with time. So, important here. So, in this case it just remains x. So, if I now take u 0 identically 0 and u 1 equal to x, then the solution is given by x t, x times t. Okay. And similarly, if you take these as initial values u 0 and u 1 both sin x, because they are arbitrary, we can take any C 2 function and C 1 function respectively. So, here I have just taken the simple function, so that we can do the computations easily, that is the only reason. So, you should practice with lots of simple examples where you can integrate easily. Okay. So, in this case, so D'Alembert's formula gives us u x t equal to sin of x plus c t plus sin of x minus c t plus 1 by 2 c integral x minus c t to x plus c t sin eta d eta. So, if you work out that, then you get the solution as sin x plus sin x cos t plus c inverse sin x sin t. Okay. So, you also, I did not mention the inhomogeneous equation here. So, you should also try that. So, taking instead of 0, you take some f of x t, where you can integrate it easily and see how the Duhamel's principle works and write down the solution. Okay. So, this is for the D'Alembert's formula. And then we discussed equations with distinct roots and also multiple roots. So, here I have taken a simple example of third order equation. So, as you see here, so this is a double characteristic part. So, del t minus c del x square equal to 0, and here there is only del t. So, you can say that one speed of propagation, simple speed of propagation 0 and double characteristic with speed of propagation c, taking c naught equal to 0, okay. C naught equal to 0, otherwise it will be just del t cube. Okay. So, just an illustration how the solution looks like in comparison with D'Alembert's formula. Okay. So, one way of obtaining the solution is make the substitution v equal to del t u, and then v satisfies this double characteristic equation, and this we have already seen that a general solution of for this second order equation is f1x plus ct plus t f2x plus ct, okay, and that is del tu. So, we have obtained v is nothing but del tu. So, now it is only differentiation with respect to t. So, we just integrate that. We integrate this del tu equal to this expression, and now you realize that this u is given by f1x plus ct. So, you integrate only with respect to t, okay. So, x remains the same, okay. So, there is, and this f3x is added because that is constant as far as t derivative is concerned. So, instead of just a constant, we can add a function of x because it is differentiation with respect to t. And now, you plug in the given initial data. So, u x 0 equal to u 0 x, the first derivative with respect to t at x 0 is u 1 x, and second derivative with respect to t is u 2 x. And if you substitute in this general formula, general expression of the solution, then we get 3 equations. Okay. They are simple, linear, but you have to really be careful in determining this f1, f2, f3. Okay. And once you determine f1, f2, f3, you plug in this general expression. So, I have left several steps for you to work out, and this is the final solution of that equation. Okay. So, you see that because of this double characteristic nature of the equation, we require more smoothness of the initial condition in order to obtain less differentiable solution, again loss of regularity. So, we require u 0 and u 2 to be C2 functions, whereas u 1 is required to be a C3 function, okay. And then the solution has required smoothness, namely twice differentiable with respect to x and thrice differentiable with respect to t. So, you remember here the equation that, so we require u to be differentiable with respect to t 3 times and with respect to x only 2 times. Okay. And just now we discussed the first order system. So, here I have taken a simple 2 by 2 system. So, here matrix is 3 minus 1 1 1. A has only one real eigenvalue 2. So, that is real eigenvalue. So, this equation is hyperbolic, whose algebraic multiplicity is 2 and geometric multiplicity is 1, and let C be this matrix. So, this computation of this C, how you obtain C, you have to work out the eigenvectors and generalized eigenvectors, and then we get C inverse A C is just this Jordan block 2 2 1 0. And now, as we did, so we write the V equal to C inverse U, and so the two components of V 1 V 2 of V, they satisfy these two equations. So, equation for V 2 is a first order equation which is homogeneous, whereas for V 1 it is inhomogeneous, where V 2 appears as inhomogeneous term, but V 2 is determined by the second equation. So, that V 2 is known. So, if you work out again by method of characteristics, so I have written here the final solution. Okay. Let me just complete with one Fourier method. Okay. So, this is taken again a simple example here. So, wave equation in a finite interval with initial conditions on the interval 0L and then boundary conditions on x equal to 0 and x equal to L. Okay. So, here I have taken this. So, physically this describes the motion of a string which is tied at the ends 0 and L. So, here it is 0 and L and plucked in the middle to a distance of u0. It can be below or above. So, I have just drawn here. A typical method separation of variables follows. Okay. So, if you work out, so just look at the workout here. So, my comment will be on the final solution. Okay. So, if you work out in this particular case, so you have to do some hard integrals here. They are not so hard, but still one has to work out, and the final solution in this case you get it this. So, remark is that u is not a C2 solution. Okay. So, this is limitation of the separation of variable method. So, though a nice looking formula, we cannot claim that u is a C2 function, because generally in this infinite series we rely on term by term differentiation, and if u is C1, that is no problem, because if you differentiate once, so still there is one factor left here 2k plus 1, and that makes that summation convergent. But when you take the second derivative term by term differentiation, this 2k plus 1 square vanishes completely. So, we are just left with sine and cosine, and that we cannot make out whether convergent or not, and it is not. Okay. So, u is not a C2 solution. So, in general you require more smoothness on the initial conditions in order that the separation of variable method works. Okay. So, you should keep this in mind, whereas the D'Alembert's formula and similar things we described yesterday. So, they do not require more smoothness, but of course, we cannot obtain a solution in a closed form. That is the drawback there, but the drawback here is this one. So, with this I conclude this chapter on one dimensional wave equations. So, in this few lectures we have covered some aspects of 1D wave equation. So, in such a short span, it is not possible to cover all the aspects of even 1D wave equation, but since we would like to show you all the important equations, namely wave equation, Laplace equation and heat equation. So, we will do these things in more detail maybe in a next course. Thank you.